All right, so last time we got through trajectories and introduction to control systems. We talked a little bit about block diagrams and how this kind of relates to everything we've been doing up till now. And at this point, what we've got is you've got a system where you can say there's some input U. It's going to go into a block that's described by some x dot is equal to f of x and u. And it's going to output something. That's our output. And at the moment, we just said it's outputting the state x. Later on, we'll assume that we can't always know absolutely the state x. And we'll add in an extra thing where we say, hey, look, there's actually some observations we get by measurements, which is going to be equal to some other function g of x and u. And then we'll say the output's actually y. So that's the most general part of the control problem. But it turns out you can solve this assuming you knew x, and as long as this allows you to estimate what x really is, that they're separable, i.e. you can do them in whatever order you want. As long as you do them both, you're fine. At the moment, we'll just assume we've got the x dot. But I just mentioned this for completeness. If you happen to look on something, you know, they will often give you this as the entire setup. But for our considerations at this moment, we've got this. Now, when we consider this setup here, if you think about this one for a sec, this is saying I've got to have some type of a, signal that's coming in. It's coming into a differential equation. I've got to figure out what the state is. That means I've got to solve a bunch of differential equations. That's, it's not impossible, but it's a lot of work. And the question is there an easier way to solve this? I mean, it's a reasonable question. Anything I'm going to do a whole bunch of, I would like to find out what's the easiest way to accomplish this. And it turns out there are a lot of really good ways to solve this. However, the one that actually is going to be most important to us is what we're going to talk about today, which is the Laplace transform. So this is based off transform theory as it goes on. I'm sure everybody, since you've been getting a little bit of math history from me on here, it will not be too much of a surprise to you if you find out that Euler actually started this whole thing. And, of course, Euler wrote up some stuff. He said, oh, this would be a great way to solve differential equations. And from that, Fourier and Lagrange and then ultimately Laplace came in and systematized what Euler said was trivial, which probably was trivial to him. But to everybody else took about another 100 some odd years to run it out. But we would like to simplify this whole thing. It turns out by going into the frequency domain, this will solve a lot of our problems. And so that's what we're going to do. So today, I'm just going to talk about properties and using the Laplace transform, because some of you might have seen Laplace transform and some of you might not. So since I don't know where everybody's at, and I'm presuming I've got a mix.
Yeah. Spell Laplace.
Well, I'm dyslexic, so I probably spelled wrong, and I'm not.
Nope, that's it. That's correct. Okay. It's Laplace.
Yeah. That's what I always say.
Wrote it down like that.
With their French,
Laplace.
Yeah, I know. It you would figure it's got to be much more difficult.
Yeah. Right.
French, but they just, they would probably just say I shaped my letters badly, which they would probably be right. I fully admit that I have sloppy. It probably should be, since he was a noble, it probably should be very flourishing.
Spend 10 minutes on just drawing the L.
All right. Well, he is a brilliant mathematician, deserves a little bit of credit in his fancy writing prose. Okay, so this is kind of our idea. Now, I've mentioned before that there is a few ideas in mathematics. And one of these ideas is when we want to kind of alter things around, it's a good idea to pick a new set of basis functions. And you can expand your functions in any type of basis you particularly want. Well, this was one of the big advantages that we got when we took a look at how we could rewrite, gain our force equations and things of that sort by taking energy and its derivatives. And that was one way we were looking at it. We dealt with general coordinates and things of this sort. Well, one of the neat things about this is we say, hey, look, instead of just expanding the polynomials, which is what you're used to doing. I mean, we always think of pretty much everything in terms of polynomials. The first thing was, Fourier was able to systematize it with dealing with sines and cosines and things of this sort, trigonometric functions. The reason why he considered trigonometric functions was he was taking a look at a very simple problem, which was, imagine you had a torus, right, or a donut. if you prefer to think of it that way. He was saying there's a heating problem, right? So I'm trying to figure out what the heat distribution is inside this torus. Okay, now since you shouldn't have an area where it's like, 1,000 degrees and right next to it's 0, we assume that the heat is, kind of evenly distributed out, so there'll be no sudden jumps.
An equilibrium.
Right? Well, but I'm not assuming that it's constant throughout.
Okay.
But I'm assuming anything nearby, they'll be smoothly distributed. So I can be really hot here and really cold here, but it's going to have to somehow smoothly transition. And he said, well, that means no matter where I pick to start this thing, when I go from this side around, it had better end up to match. And he's going around a full circle. Well, what type of function matches at the other end? Well, trig functions do. So I said, well, look, trig functions meet my matching requirements, so no matter where I start, I'm guaranteed to get this nice fitting. So I said, trig functions make a lot of sense here. And so that's what he expanded in. Euler, when he did generally. So, he actually considered much broader ones than it was, but he didn't pursue it extremely far because he said, oh, this is kind of simple. Damn him. Now what Laplace did is Laplace kind of tried to extend this as it goes, and he actually came up with one of the fundamental insights. This is one of the few times that Euler did not completely punk the area. Laplace said, well, look, instead of just writing the answer in terms of these integrals that we're going to get to in a sec, he said, let's just transform it, solve it in there, and transform back. And that observation is actually what makes it simple. And that's where a lot of the speed that comes on in these transform techniques go. But he also considered here, instead of just matching sinusoids, we've also seen in physics there are sometimes you get these damped sinusoids. You'll sometimes get, here is your time and this is the displacement of the function. And you would get an envelope that's kind of decaying down, and then you'd have a sinusoid that's kind of bouncing inside it. It's like a ringing bell that slowly damps down. Right, now you can see there's obviously trig stuff, but it's damping down. Okay. So, and this outer function here usually looks something like, e to the minus at, where a is some positive number. And that's based on whatever your damping coefficient is. That describes how, in essence, you are losing some of the energy in that system. So, and that's your damping, and that's, nice and all that. And he just said, well, look, this means that your general solutions look like that times those sinusoids. But sinusoids look like e to the minus j omega t, something of this sort. So he just stuck them together. And instead of, the a, he puts in a sigma. But in essence, what he gets out of this is he gets damped sinusoids. So he's going to consider his basis functions as, e to the minus st. That's the basis function he wants to go. Where s looks like sigma, and you can do plus or minus j omega as it goes on, right? The point of this being that you've got complex numbers here. There's a real value that describes the damping. And then there's an imaginary value that describes the frequency of oscillation. Fair enough? So that's kind of where the motivation proceeds historically. And it's one of the few times I think historical actually gives you a good idea of what's going on. The fact that I'm allowing this extra damping allows me to actually solve more problems with Laplace than I can with Fourier. Right? So Fourier, and the reason why is we're about to define an integral. Well, in order to solve something with an integral, the integral has to exist. But I'm going to be integrating across infinity. So when I'm taking an integral across an infinitely large domain, it is possible that integral might run to infinity. If that integral goes to infinity, it doesn't converge. And so therefore you have no answer to that integral, so you can't do anything with it. This is where the Fourier one runs into some problems. Well, the advantage that you have with Laplace is I also have this damping coefficient. Because it allows this to run down to 0, whereas with Fourier, it's constant. It's always magnitude 1 the whole way through. This one has a smaller and smaller, so it's converging to 0. So that allows me to deal with things that are not themselves converging to 0. Right? They can actually have an infinite length as long as they don't grow faster than this one is shrinking away. And so, therefore, I can solve more problems because more integrals converge. That's really where the thing comes in for us.
That one doesn't actually hit 0 though, right? It just...
But it approaches 0.
Okay.
Right? In the limit,
We're talking about
it's 0.
Okay.
So it doesn't hit 0 in the reals. But in the extended reals, which includes infinity, it does.
Okay.
And a lot of weird things happen in the extended reals. Like one way that you can define parallel lines is 2 lines that only meet in the extended reals.
Yeah.
Okay? And that one usually blows a lot of people's heads because I'm saying they can actually meet, but you can actually show they can meet in the extended reals and still be parallel.
Can or do?
Yeah, you actually show they have to.
They have to.
Yeah. So
Well then.
that gets kind of ugly, and I don't want to go into all those things. You know, if somebody's interested, I can show you afterwards. It's not particularly long to give you an indication, but I don't want to get too sidetracked.
All right.
But what I do want you to do is to understand there's a lot of neatness inside the mathematics here. And there's a reason why we're going to bother to do this, and there's trade-offs for it. The Fourier one, since it's more specific, will be able to give you certain nice features because it's more specific. More specific allows you to show certain extra properties. The more general you write it, you have less properties available to you. It turns out Laplace still has pretty much all the good properties, but happens to converge for more things, which means it works for a broader class. Now, so that's one thing. And you'll see these they'll talk about regions of convergence. The big thing that you will see within their regions of convergence, and I'll show this one in a sec, but let me at least introduce it while I'm going through here. If I look at the complex plane, so complex plane in our mind is now sigma, the real value, and then I've got, my omega variable running up this way. And so if I'm looking at those as I'm going inside the complex plane, there's going to be certain points where there are infinities. Okay? We call these poles. And it turns out your region of convergence can never contain a pole. And I will show you what that means when we get into the complex plane, but I'm talking about now, so I at least want to mention the idea. And the location of these poles like this are going to be absolutely essential to where the performance is of the system. As a matter of fact, I can just look at this and tell you this is unstable.
No problem.
Yeah, you cannot have poles in the right half plane. They all must be in the left in order to be stable. So it's a real easy one. If you ever see anything to the right of the origin, it's unstable. But there's a lot of nice features like that. There's even more. We can tell you what frequency they'll oscillate, by what location it's at, things like that. So, but the point being that where these are located, and this is going to be fundamental to where we get them, we'll tell you cannot converge for them. Well, imagine what would then happen if I have some on the j omega axis. Well, you have the ability to oscillate continually, but think about this. How exactly do I get the Fourier integral to converge when I have poles on that axis? Well, it turns out there's just one. There's some fancy tricks I can do to make it converge. But if you've got a double pole, you're dead. And Fourier can never converge in that way. For a single one, I can just sidestep it. But for doubles, I'm in much more trouble. Anyway, so that's kind of where the idea goes. It's a basic overview, where they happen, where they matter. I'm not expecting you to be experts, but at least to be aware there are issues.
Oh.
Makes sense? All right. So now I've got this as what I'm trying to expand as a basics function. And hopefully it makes sense why I care about this. I want damned sinusoids. So you now have some function, f of t. And I want to expand f of t inside of these. So what I have to do is I have to find out how much your f of t is in the direction of this individual basis function, e to the minus st. Does that make sense?
Mm-hmm.
If I'm going to rewrite a function in terms of something else, you got to find out how much of this is pointing in that direction. The way you do that is you calculate its projection. How much of that is projected into this space? Well, the definition of the projection tells me that I've got to run this from minus infinity to infinity of this derivative with respect to time. That is the definition of how much this is pointing in the direction of that. It's just the projection. What is the length of f of t in the e to the minus st direction? Okay, so I'm finding, in essence, the coefficients that are associated with these damped sinusoids. Make sense? But that means that I then have the actual weights of this function in its frequency domain, in the damped frequency domain. Well, that's all Laplace was looking for. So that's the Laplace transform of f of t. And we will often just call this by capital F of s. Okay? So if I'm going from little f of t, I go to capital F of s. That way you can easily tell what are pairs. Now, what we're going to try to do is rewrite equations that we're interested in into this form. So we're going to, in essence, get a series of things. There will be the basic function f of t, and there will be the Laplace function of f of t. All right? So I'll have, what's working here in my regular time domain and what's in my damped frequency domain, or just generally frequency domain. And we've just found the first one. If you are f of t, I can define that as capital F of s. All right? Following this interval. Fair? Okay, now we want to start trying to list some things out. And I could start saying, well, let's consider some, things that might be nice to know. Like, for instance, if this is the definition of the Laplace transform of f of t, what is the Laplace transform of f prime of t? The derivative. The reason why I like to start with this one, I don't think anybody else does, is because this one, more than anything else, tells you exactly why the hell you want to do this. Right? This, to me, is one of those key properties that's out there. So, now, as one side thing before I solve this, note, this is what's called bilateral Laplace transform. There's also another version of the Laplace transform that just goes from 0 to infinity. You will often see that one done. This is called the unilateral. Okay, it's just one-sided. The assumption behind this one, the unilateral is the bilateral, where you make the assumption that you started at some time equals t0, and before time equals t0, the system was off, which means f of t was 0 before t0. So all that just disappears. And you might say, well, that sounds like a strange restriction, but it's a very common restriction. Think if you're an engineer or a computer scientist, your computer has not been running since eternity past. You turned it on at some point, okay? And we make that turn on point, t equals 0. So this is actually the one we more often use. It doesn't really drastically change anything, but it builds in the assumption that the thing was turned off, and then you turned it on. So that's often the case that we deal with. But realize you don't have to. You can generalize it should you need. All right, so what I've got here then is the Laplace transform of f prime. Now realize, after today, you won't be solving too many integrals. But today I do want to kind of check some of your calculus areas that you go on. And this is one of those very neat things. The solution to this is either really easy or you give up. Okay? And this tells me whether or not you know a particular calculus trick. So when you look at this and you see a derivative of one function times another function, does that ring a bell as a particular style of integration? Maybe involving parts or something.
Perhaps by.
What's that?
By?
Yes, integration by parts. What's the idea with integration by parts?
You integrate one portion of it, and then you integrate the other, and then you add them together at the end.
Yeah, so what's the image of it, though? Like, most people know that's, okay, I have to do some weird, funky trade-off, but it's actually a very easy picture. You've got some function that's going on. You want to find the area under the curve. That's what integration is, right?
Yes.
If you consider the whole thing, integration by parts says, consider the entire area and subtract this side, and that'll give you this. And that's all integration by parts is doing. Yeah.
Really.
Really, that really is just it.
5 calculus classes that don't mention that one.
And they never told you. Yeah, I know. People never tell you that, but that's all you're doing. Watch when you take a look at the actual function, what's going on, right? They take this one, and they call this one du, right? They stick the dt with it, or whatever, right? And they call this one v. And then we just integrate that. Well, that's pretty easy. That means u must equal f. Right? And then I take the derivative of this. Well, what's the derivative of an exponent?
Negative s e to the.
Yeah, you couldn't ask for anything nicer. So dv has to be, you know, minus s times e to the minus st. And I'm not worrying about the dt thing. I'm just going to leave. I mean, obviously dt would have gone with that one, and then I'll get a dt from here. So I'm just not going to worry about it. And what you get is uv integrated across the entire thing. In this case, I was going from 0 to infinity. That's the total area. Right? That's the box. Minus the integral of u dv. That's this part up here. So the area under
Yes. that makes
is
sense.
the box minus the area over. I mean, it's even written in that form.
It is, yeah.
Okay? So this is why I say there's an awful lot of mathematics that's easy to understand if you understand what they were doing. Right? And if you just got presented, here's the result, then you have to memorize a bunch of junk. Okay, this is why I say never memorize anything. Because there's probably some trick somebody thought in the first place. You went, oh, this would be an easier way to do it. And if you don't get that, then you're memorizing with no knowledge. That's a pointless gesture. So this is the way to remember it as you go on. So is this getting low for people over there? I'm going to carry over to this side. All right, so I've got equals to, and then let's see, u was my f, and times v, and v is e to the minus st from 0 to infinity. And then I've got minus my u, which is f. I get the integral from 0 to infinity of f of t. And then I've got times minus s e to the minus st dt. Now I take the minus s out because it's independent. So this part here, I'll get a minus a negative s, which is just plus s. I'll deal with this one in a sec.
This is why I hate doing by parts, because now you got to do it all over again to get rid of that last one, right?
No, I don't. I'm actually done. Right? Everybody tell me what that is? That's a Laplace transform f. I'm done.
Okay.
Okay, I already know what that is. So I'm going to skip down another whole line and then I'll deal with this one. Plus s times, that's just f of s.
Right.
All right. So as long as you know what s, little f to big F is, then you just stick it right in there. No problems. How about this other side now? Well, consider when t goes to 0. Right? E to the minus 0. That's e to the 0, it's 1. So it's going to be whatever f of 0 is. So that's on the minus side, so I get minus f of 0.
Right.
When it goes to infinity, e to the minus infinity is
0.
0. That's the extended reals.
Right.
Right? So remember, in the limit it goes to 0. So that goes to 0. 0 times anything is
0.
0. That's on the positive side of it. So this is just minus f of 0.
I'm assuming for higher order derivatives, this
And we usually
expands
just
out.
write it this way, s times f of s minus f of 0. Now, let's make another assumption. We said we turn this thing on at time t0. Let's assume, just for simplicity, just to kind of draw us a simple why does this matter so much to me thing out here. Let's assume that this thing was 0 at time 0. Right? So at that point, I've got s f of s. Do you realize that I just took derivatives, i.e. calculus, and turned it into algebra?
Yeah.
Huh?
Important.
I mean, that's really what you've ended up getting here. You multiply by the damped frequency and you have taken its derivative. So I can now solve for S and find out exactly what was going on inside this system, and I have reduced everything to just solving algebraic equations. That's kind of a nice feature, to be able to completely remove calculus and just solve by what you were doing in junior high. Okay? That's really what it does for you. As long as that integral converges, you are able to solve calculus problems like algebra problems, using all the regular mechanisms of algebra you had before. But realize, almost everything we get from physics is differential equations.
Must make physicists happy.
Yeah.
Or piss them off.
No, it's actually, I mean, this is one of those things. If you're going to do it, it makes it simple. It's a simple mechanism to handle it. Yeah. So this, to me, is one of those great elegances of life. Now, the question was, what happens with higher order derivatives? You could solve it. You have to do multiple of these. But what you end up with is, you'll discover that you can nest this. If anybody took 535, we first talked about nested multiplication. Well, you'll end up with a nested situation on that. This is not the way most people write it, but if anybody's ever had me before, you'll find out I don't write things the way most anybody writes them. So I just take S times that whole thing, right, minus whatever the first derivative is. You want to add in the second derivative? Okay. If you were taking more, that was one derivative, two derivative, three derivative, I multiply that whole thing times S minus F double prime of 0. That's three derivatives. So this is, I find this one just kind of easy. Remember, I just nest them, just keep taking the previous thing, and it looks just like this is some new function g, you know, and then whack off its derivative as it goes. And so this is just f prime, so this is therefore s times f prime's thing minus f prime's derivative. All right. You want to go another one? Okay, s times the double primes minus the double prime's value at 0. You can add as many as you want that way. You will often see this written as, if I'm taking the kth derivative, they'll tell you it's s to the k times f of s minus s to the k minus 1 times f of 0 minus dot 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 all the way down to minus f of the, actually I should say, the k minus first derivative evaluated at 0. So I'll give you this sequence that goes on where you keep getting smaller and smaller s values, multiplying higher and higher derivatives. But realize that's the exact same thing. It's just written as a series.
Right.
Yeah.
Your assumption that at f at 0, we start at 0 with x and y.
So that wasn't, I wasn't saying that for general.
But
I was just saying just so it's easy to see so I don't have to deal with it.
Okay.
In general, we often will have f of 0 be non-zero. Sometimes we will, sometimes we won't. My point of it just was, you know, let's just consider this part right here, you know, because I could just say, let my initial condition be 0.
Okay.
Now, sometimes that won't be the case. My point was just to notice that the derivative becomes s times the function. And then you might have to adjust for the initial conditions. But that's really what this is.
In your integration by parts,
Yeah.
the infinity term is 0. So in a bilateral Laplace transform, does this get even easier and they're both 0, so it's just always s?
Well,
at
you have a negative, so you actually
Except-
have e to the infinity, not.
Yeah, so what you would end up with as that's going on, realize if you're going to e to the minus infinity, you're saying it's been around for an infinite period of time as it's going on. And what you would end up with is e to the minus a negative infinity, which means this term is growing really fast. Right? But then the question is, how fast is this one damping out as it goes on? It had better be damping out faster than that.
Right.
So it either goes to a constant or whatever else. If it goes to a constant that's not equal to 0, that's kind of like whatever the potential is right at the, you know, negative infinity point when you kind of assume it launched. Right? If it goes to 0, then you assume it was damped on either side and something fun happens in between. Cool. But this one is often the case we do because we just say, hey, look, we know what it was at this point. And I had said, you know, we turned it on. But realize I turned it on is also equivalent to saying this is when I first noticed it, and that was its starting condition. Right? If I have a pendulum and I release the pendulum from here, right? And it starts swinging. You cannot tell if that pendulum was swinging from that position I released it at or from an hour before, a little bit further out, right? I mean, it could have been swinging longer just with a little more amplitude to start with, and it just damped down. As long as I release it smoothly, I should be able to project it back as far as I want. So I can also just take an initial starting condition that's going on that's consistent with your system and then handle it that way. So that's another way you can think of the unilateral as kind of a nice one. We very often, can't say I can extend it back infinitely, because I mean the universe doesn't even extend back infinitely. What was the condition at the Big Bang? Right? These are kind of difficult ones to go on. So we assume pretty much everything we deal with had, some finite time start, and we know what that condition was. Right? And it makes it calculable, and that's why I say theoretically the bilateral is true, and you could solve things in general for that. But in general, we usually actually just do the unilateral because it better fits our things, and it includes those initial conditions that allows us to fit to a practical system. But those are good questions, right? Okay, we feel good with this? So we've now solved kind of a fun thing, and we now have a property derivative. And you can extend this one, right? If you want to think about higher order derivatives.
Yeah.
And you're welcome to write them in if you feel like it. But I think if you understand this one, what it's saying, it's pretty easy to extend. Good so far? So let me kind of hammer home why this matters. This is why I say this is such a wonderful thing to us. Let's consider mx double dot plus cx dot plus kx equals some function of u, a forcing term. All right? Make sense? Okay, and maybe I'll just even say, hey, look, what if I know my u, the forcing term, I just know f of t. I just know it in terms of time. This is exactly what I'm going to stick into the equation. Maybe I'm going to drive this thing with a sinusoid. Or I'm going to drive it with a step function. I turn the power on and let the power keep going to it. Or I drive it with an impulse function. I just hit it once and watch it ring. So, I mean, I can just say I know what the forcing function is. Fair enough? Well, let's consider what the Laplace transform of this is, right? Because this kind of still looks a little bit difficult to solve. Well, we say that little x, implicitly these are x of t that's going on here. So we say that x of t is going to map through the Laplace transform to capital X of s. So therefore, what I have here is, let me just kind of work from these terms and work this way. I've got k, that's just a constant. This is x of t, so when I take the Laplace transform, it's going to go to x of s. We agree? How about here? Well, this is x dot, right? So I've got to have on that plus c times x dot, but x dot just goes to s, x of s, minus x at 0.
So what was the C again?
C is your viscous damping.
Okay.
Most often that's like air drag. And I use C for that because C is the common one used for air drag. So if you ever take a look at an aerodynamics equation, the drag coefficient is C. So since that's the most common one that is proportional to your velocity, is drag, but it's any type of a drag thing. All right, so I just replaced x dot with its definition. Right, we already said in the table, right? The derivative of your function, derivative of my function is s times the transform minus the original time domain function evaluated at 0. I'm doing x as my function now, so it goes to s times x of s, the Laplace transform of x, minus the value of my function x at 0. Fair enough? All right, now I get this one. It's m times this one's transform. Well, x double dot, I just nest it, so it's going to be s squared of x of s minus s times the value of x at 0 minus x dot at 0. Fair enough? All I did is kept applying the rule. Trying to show it works. And that has to equal to this one's transform. Let me just call that f of s. Whatever the transform is of your forcing function. And eventually we will have a table that just says, here are Laplace transform pairs, and we'll just substitute it in. Now, consider what's going on in here. There's no longer really any derivatives. You say, well, look, there's a derivative there, but it's derivative evaluated at a point. I'm just saying, what was the starting velocity? So I'm not actually having you calculate anything. Just saying, how fast was it moving at time 0? That's a single measurement. So you don't have to do any calculus there at all. You stick in a number. Right? So all these ones here, this is just initial condition, initial condition, initial condition. They're just values. So that's fairly simple. We'll just use distributive property first. So I get ms squared capital X of s. I'm just multiplying through. I'm going to put all the ones that involve x of s here. I'm going to put all the ones that don't over here. Fair enough?
Yeah.
Okay, so then I'm going to get m times minus s x here. So I'm just going to, we got a lot of minuses with all these initial terms. I'm just going to put minus outside, and I'll just get m s x 0. That times this. And then m times this gives me plus m x dot at 0. That's this times this. Remember, the minus sign's already outside. This times this gave me this. This times this one gave me that. This times this one gave me that. Well, a lot of people are staring at me like, you know, the coffee machine broke and I'm speaking in, you know, Swahili or something. Right?
No, I was
so,
redoing the
okay.
part of expanding in my head.
Okay.
Distribution's easy. It's the expansion.
Okay. It's just when people stare at me like, you know, I kind of like, okay, what's up?
That's just my excited face.
I know, yeah. Woohoo, raise the roof party. And nothing gets a party going like doing transform theory. Yes. So, yeah. All right, so next term, plus C, S, X, S. That times this. This is my initial condition, so I'm sticking in here. Minus C, X, 0. We agree?
I feel like we're going to throw this into a matrix.
Plus K times XS. Realize I don't actually have to throw this one into a matrix. We can actually, but I don't need to. This is kind of the cool thing about this as it goes.
Minus the number. It's all
Right.
nice.
So I've got this. Now, all of these terms involve capital X of S. Let me just pull it out. ms squared plus cs plus k times capital X of s minus a whole bunch of initial conditions. Right? ms plus c times x of 0 plus m x dot of 0. I just grouped these two together. So far so good? And that's got to equal this. I haven't changed anything at this point. Take this to the other side. I want to know what XS is. And then I'll divide by this. Is it okay if I do both in one fell swoop?
Yes.
Hey, you said yes. So, so I have f of s plus ms plus c times x of 0 plus mx dot at 0, all divided by ms squared plus cs plus k. I got a closed form solution for what is x.
Awesome.
Once you get this closed form solution, you just take its inverse transform, and that gives you what x of t is. Realize I just solved your whole differential equation in a couple lines by using that rather tricky distributive property. All right? I mean, you gotta admit that's a little bit, I mean, you looked at that in a standard calculus class, it would be a pretty ugly thing. But this is downright elegant. I mean, it's almost so simple that people go, no, it can't be. Right? So it's kind of nice that we can actually get closed form solutions to this. So this is why what we will typically do is actually express inside those boxes, we'll just put the Laplace transform of what the output's going to be. It just turns out this is the nice way to write it. So I've actually got the solution. I mean, this is the answer.
Yeah.
Right? Then all we need is, then you take this is on the x of s side, you have a big long table, and we have tables and tables of this stuff. You just look it up on this side, combine together with the properties, and figure out what f of t was. That's just a big lookup. It is nothing more profound than that. And I just solved, I mean, that one was, mechanics, but, I mean, you could go through and substitute in, the various, capacitor, inductor, resistors, and you just solved all of electronics just by changing the letter names. You can go through and put in the associated hydraulic parameters, and you've solved all fluid mechanics. Except for the partial differential equations, which are slightly different, but all the ordinary ones you've solved. I mean, it really is that nice.
Would it work to, so say you had second order ODE, would it work to change the integrals into differential equation or into derivatives and just solve it out?
Well, that's what we just did. It's a second order ODE.
Yeah.
I mean, that's what that is.
Yeah.
I solved that in general for any old Newtonian system that involves mass, an atmosphere, and springs. Right? So, I mean, remember when you did physics, they said, let's neglect the atmosphere because that's complicated. I didn't. Okay? And we solved it in a few lines. This is the power of math once you get into it. So realize it's very nice stuff as it goes on. Good?
Yeah.
So that's why we like it so much. This property is gigantic. Now, for those of you who have to do Fourier transforms in some of the physics courses and that, all you have to do is replace s equals j omega, and you get the Fourier relation. So just put, in here, just do a fancy f, and just go j omega, j omega, j omega, and you just got the Fourier values.
Lovely.
So you get Fourier for free. You just choose sigma to be 0. All right, good? Mm-hmm. Awesome. Let's take a look at some other wonderful things about this.
Are you going to run through another example of expanding it out, or?
I'm going to go to another property unless you want me to.
If you can, that'll be just going to maybe expanding it out to different equations.
You want to look at
So I can do it like inductor L and just substitute through?
Sure. Maybe a little easier than I thought.
Well, honestly, to go to the electronics, that's all it is.
Yeah.
Right? You just go L, R, C. Substitute through. There you go. I just solved all, inductor, capacitor, resistor. I mean,
Yeah.
This is why we like this. Right? Transform techniques are a simplification because what you've done is you moved it into an easier domain where it's a little more natural. You've solved it in its more natural framework. And then you bring it back to whatever yours is. Never assume your first way of writing it is also the easy way of solving it. Okay, life is full of trade-offs. What's easy to write is often tough to solve. So once you've figured out how to write a problem, then you've got to figure out what's the easiest way to solve it. Well, for differential equations, this is pretty much it. I mean, it really does not get too much simpler than this. So, I mean, honestly, for differential equations, I could write as many differential equations up here as you want, but I solve that one generically. I mean, all you have to do is substitute values, change the letters. So, I mean, if there's a particular, I mean, if you want to take a look at higher order derivatives, you can write higher order if you want.
Oh, no, I just, the process of breaking it out.
Yeah. I mean, if you want another fun thing, we could do that, you know, a similar type of a second order thing and rewrite it as first orders with a show it works for vectors too. We can do, I mean, because realize when I did this, I didn't say whether f was a scalar, I didn't say if it was scalar or if it was vector. So realize it's irrelevant to me in that case. So I could have taken that same type of thing, and remember we had x dot as it goes on, and we said that that was equal to some type of a matrix A, and we take its derivative times x dot. Let me just do this part, we'll not worry about the forcing function on it as it goes on. When you take the Laplace of this, you know, this, we call this state x dot some y. Realize this is just y dot equals ay. Right? Where y is a vector, but who cares? Right? No problems to me. So, what's the Laplace transform of y?
Y, big Y.
Well,
That's
it's
what mine
s
said.
times capital Y of s. Laplace transform of that vector. Minus my original y, evaluated at 0. Right? And then that has to equal a as a constant times y, which is its transform as capital Y of s. This is a vector equation to do the same basic lovely thing that goes on. So now I have this, I say, well, look, I just want y of s. So I'm going to take, I want y of s all on one side. So what I'm going to do is I'm just going to take this one over to that side as it goes on. I have my minus y of 0, and that's equal to a minus si times capital Y of s. I did distributive too.
Yes.
All right, take this to the other side. All right, so you get minus s times y of s.
Where'd the I?
This is a vector,
Oh.
right? This is a matrix. You can't have matrix minus a scalar. What did that even mean?
Yeah.
Right? I mean, if I told you 1, 2, 3, 4 minus 5. I have no idea what that means. I have no way to calculate
That's
that.
the 5 matrix, don't you know?
You know? It doesn't make sense to take a matrix minus a scalar. But what I had was I didn't have that. I had this times some vector, you know, capital Y, and this times some vector, capital Y. Well, you always have any vector times the identity matrix is back to the vector again. You can always do that. This is the matrix equivalent of saying multiply by 1. Okay? So this is completely the same exact equation. It hasn't changed anything. Now when I distribute y out, I get this minus 5 times I. I know what that means. Subtract 5 from these two components. That's simple. It's well defined, and it is completely consistent with the original equation. Whereas if you didn't do that, you would have something that was inconsistent. So when you do a distributive property, you got to remember, you have to do distributive property over the elements it's allowed. There's no distribution of matrices, you know, and scalars that's inside the same area. But matrix times a vector, yeah, that's perfectly fine. So the I is just the identity and allows me to have a consistently written equation. Okay? Good?
Yep.
But I want y of s. So now I also have to, but this is a matrix.
Multiply by the inverse.
So I multiply by the inverse on the left-hand side.
Yeah.
You know, and remember y0 is a vector, so that's no problem. So that means my whole answer to that now is equal to minus, and I've got A minus SI inverse times Y at 0. That's equal to capital Y of S. There you go, we just solved any old vector equation you wanted. They all take that form. This is actually the one we'll do more of. And the reason is, I mean, I did this for, you know, x and x dot, but realize I could have x, x dot, x double dot, x triple dot. I could have as many powers as you wanted. You know, I could have had x, x dot, z, z dot, you know, Fred, Fred dot. Yeah, I could have made that vector as big as I wanted going in there. And I could have just called that whole thing y. Away I go.
Why not?
Why not? Now, the other fun thing that goes on here, if you notice, this is an eigenvalue problem. Well, that's the eigenvalue and that's the eigenvector. So really, when you are solving these equations, you are doing an eigendecomposition of the frequency domain. That's all you are doing. Right? So, and that's why this, remember, eigenvalues tell you the oscillations. Remember, S is our frequency space. It tells you the oscillations. And the eigenvector tells you the general shape parameter, and that's exactly what your function y is. It's the shape parameter. It's the shape of your output function. It's completely consistent conceptually as an idea. So that's actually all you are doing, is transform into frequency, take its eigendecomposition, and make sure that these values, we call these values of S, they are the poles. Remember I told you that we would encounter poles fairly soon?
Yeah.
Well, you have now encountered them. You might ask, why do I call that a pole? Well, consider the point where this function here becomes 0. This is an inverse. It's 1 over that. What's 1 over 0? Well, it goes to infinity, right?
Yeah.
I mean, it's undefined in our regular real numbers because infinity is not in the reals. It's in the extended reals. But it goes infinite. As you get closer and closer to 1 over 0, it gets steeper and steeper. But it's undefined in our space for the actual value that it hits. The value of S that makes this equal to 0 is the eigenvalue by definition. So that's why the eigenvalues are the correct choice that's in here. And so we call those eigenvalues the poles. So when you find the eigenvalues, or the poles, whichever you like to call it, it tells you the characteristic oscillating frequency. That's really it. That's physics and engineering in a nutshell. Okay? We just like to wait 4 years to tell you. Okay? It justifies all the rest of that money, and you now feel very appreciative of this simple equation. All right? Do you see the power of why this one little property is just so magnificently important to us? I mean, this is really a triumph of math. It really is. And trust me, there's math results beyond this that are also equally powerful to us in different areas. That's why I always say, take math. It will always help you. Good?
Yep.
Awesome. So, do we need more examples, or?
I'm good.
Yeah, if you think about it, this is, vector calculus in a nutshell. Right? So there's a lot of fun stuff we can do from this. All right, so let's take a look at some other fun things we can do with this. Maybe we should develop some actual direct solutions to some of these, some transform pairs that go on. There's a couple other properties I want, but I'd like to at least make sure I get through a couple real transform pairs. So let's assume that we've got, let's pick one of my favorites. I always like this one, delta t. This allows me to emphasize a neat property. Delta t is what's called the impulse function. Okay, it's sometimes called the Dirac delta function. There's a lot of different names for it. Now, the importance of this particular function is, it's called an impulse function for a reason. in physics, you know how they talk about, you get some impulse and it conveys some momentum to the system. And the impulse is just, boom, just got hit instantly. You assume that it was just instantaneous hit and it transferred, into it, this impulse to cause a momentum in the resulting system that goes on. It's just kind of ringing the bell with a gong as it goes. Well, we do that kind of thing, don't we? Don't we sometimes just hit something? Just give it an instantaneous hit and then see what happens to the system? And there's an awful lot of cases where we send a single little pulse down the line in our digital things. We turn it on and off. We say that creates a pulse. There's your pulse. So this is something that's kind of important to deal with. But ideally, this pulse should be 0 everywhere except at that point. That would be a perfect pulse, wouldn't it? Mm-hmm. Now, let me ask you, how do you now handle that with Riemannian calculus?
Very bad.
There's a real short answer. You don't. Riemannian calculus cannot handle this. Okay? First one that can handle this is Lebesgue integration.
And that's because it's a discontinuous function, really.
It's a discontinuous function. And it's kind of a neat thing. I mean, the difference as a real shorthand thing, Lebesgue integration, instead of Riemann kind of chops things up this way, Lebesgue chops them up this way. And it turns out that makes all the difference in the world. Remember I told you how you look at a problem, small transforms sometimes have profound effects. That's really essentially what's going on.
Because that could handle an instantaneous jump then?
Because you're discretizing the actual resulting. Yeah. So this is equivalent, when you go into 535, we talked about different ways you can solve integration. I said there's this really cool method where we discretize the domain, the range, instead of the domain. And it's really converges, has much better convergence properties. That's really Lebesgue integration resulted from that.
So all he did was take a look at Riemann and he's just like, well, what if we chopped it this way?
Yeah. And he actually explains it that way. He says, he gives an example in a letter where he says, imagine you were paying off a debt to a friend, and you got a bunch of money in your pocket. Riemann integration is, I pull out a coin, and I keep pulling out coins until I have paid you off. Right? He says, my method is you pull it out, you sort them, and you hand them the pile. That gives you the correct answer.
Right.
Right? But because it's sorted, you shouldn't be too surprised. In an awful lot of areas in computers, right, if you sort it and then solve it, you get a much better solution than if you don't sort first.
Yeah.
Right? So don't be too surprised that changing that, in essence, sorting under a different domain, alters the properties of what's going on. It just turns out when we write things, our ending area, the range, is often much nicer behaved. And for instance, I actually described to you what the range looked like here, didn't I?
Yeah.
When I defined this, I defined the range. Did I tell you too much about domain properties? No. See, that's the problem. When you go to generalized functions like this, I often know the range and can discretize in the range, but I don't know the domain nicely. So it really makes a huge difference on how you discretize the system. All right. So enough on a side thing. That's just if you like to know what the heck you're doing. It's a small change, and it has a powerful effect. Let's now consider what's going on. The way we're going to define this function is we're going to define that delta to have a certain area. All right, so that's an integral from minus infinity to infinity of the delta function with respect to t dt is equal to 1. We're going to define it by its range, right? Which in our case is what's the area under the curve, right? So I just said the area under the curve is 1. Realize I haven't told you what the value of the function is at that point. As a matter of fact, in a way, I kind of have. I told you that it's 0 for everything except for t equals 0. So if it's 0 everywhere except this one infinitesimal point, but the area is equal to 1, what's the width? It's 0. 0 times something equals 1 is what I have just told you.
What?
There's nothing wrong with that. right? The only time you have 0 times something is always 0 is in the reals. But that's not true in the extended reals. Remember I told you, you go to the extended reals, and an awful lot of your intuition goes out the door because you don't think in terms of the infinite.
The value is infinity of that.
It's infinity. It's the only place that it can be true. It has to be infinite. Okay? And that's why we say those spikes. Right? In essence, you could have a lot of power under that even with a spike, because what matters is what's the area under it. Okay? And so any amount of duration, we usually, to prove that, you usually just take, and you take something like this and you make this epsilon, and you let epsilon go to 0. Right? Which is going to force this one to go up. And you just define this area to be 1, which means you define the height. Right, so this thing right here, if you make this height here 1 over epsilon, what's the area?
It's just going to shoot up.
1, right? This is 1/2 base times height for that triangle, plus 1/2 base times height, so it's base times height. Epsilon times 1 over epsilon is 1. Now take the limit of 1 as epsilon goes to 0. It's still 1, right? So, but this went to 0 and that went to infinity. That's why infinity times 0 can be a finite number. Right?
Yeah.
Right? It's- by definition, boom. Right? So a lot of your intuition goes out the window, but you got to realize, hey, it's okay. You got to redefine your intuition. Right? Your intuition was built up of very simple things that you were playing in a crib with. We need to go beyond cribs. Okay.
Can I at least keep my nightlight?
Yes. Night lights are wonderful. But this guy, I mean, it's the first time you really hit mathematics that doesn't really, at first glance, make sense.
Yeah.
And then all of a sudden you go, oh, right? That's your mind growing. So it's kind of cool. Okay, so when we do this, there's a lot of neat properties that result from that definition. One of which is, now consider if I took delta t times some other function. Right? Right? Now, I don't know what the height of that is, but I know what its area is. So if I consider the integral of that, then this area is 1 times that, but this only appears at 0. So what I get is f of 0.
Yeah, 1 times that.
It samples the function. Okay? If you think about it, it's got to. So, you know, this is a neat property which we're about to use. So that's why I need you to kind of understand where this comes in. You just realize this only has a non-zero value at 0. So that means only this at 0. So when you consider my little original triangle, I now have 1 over epsilon times f at 0. And then times epsilon. So what's the area of that? Well, it's epsilon times 1 over epsilon is 1 times f of 0. So the area under the curve is f of 0. Take the limit as epsilon goes to 0, it's still f of 0. Okay, so it's pretty easy to see that's got to work out. We agree? All the other values of f are multiplying 0, so they just get wiped away. No worries. Good? So that's kind of trivial. So keep that one in your head. Now we can write them. Let's take the Laplace transform of this. For the Laplace transform, we're just going 0 to infinity. But realize 0 includes the point 0, and that's where that thing is defined. So I'm fine with that. Of delta t e to the minus st dt. That's the Laplace transform of the delta function. But we already said delta function times anything integrated across the area that contains the non-zero point is just sample the function at that point. So this has to be sample this function at that point. So e to the minus s times 0. But minus s times 0 is?
Well, 0 and then
It's 0 and then e to the 0 is?
We jumped ahead of it.
It's almost anticlimactic once you understand the definition.
Yeah.
Okay? But realize it was able to very easily handle it, wasn't it? So that is your delta function. It kind of functions like our 1 value, but there's a neat implication of this, which, by the way, actually gives you an awful lot of quantum mechanics. And this is why this becomes also important for them. The delta function is sampling something at an exact instant. I know exactly what's going on. And this one is saying that in the frequency domain, it's a constant. Okay? Now think about the implication, because this is also Heisenberg uncertainty principle. If you know the exact thing in one domain, you don't know squat diddly about the other domain.
Right.
If you consider probabilities, probability of knowing your location in space, right? So now make this your spatial domain, and this is a 1 over, this is a frequency.
Yeah.
Well, space divided by time, the frequency equivalent of the spatial domain, that's your speed, times mass, it's your momentum. Right? So this is exactly what Heisenberg and said. If you know the position, you have no idea what the momentum is.
Yeah.
Okay? And that's what it's telling you. You know one exactly, you know squat diddly about the other. Now notice, this does not involve anything whatsoever about how I measured it, does it? Okay, so if anybody ever tells you quantum says you measured it, and your measurement interfered with it, and therefore you can't get it accurate, they are dead wrong. That is just not true. It is mathematically impossible. If you know this, the distribution of the probabilities is such that you cannot know anything. Okay? It's just unknowable. It's not a measurement interaction problem. It's a fact that you know this exactly. In order to make that sharp of a thing, you have to have all the possibilities over here of momentum. If I'm running full speed on here, to get a dead snapshot of exactly a location I'm at, you have to have a crisp edge, which is an infinite series of all the possibilities built up. You need all of them. So you cannot possibly know my momentum. Every little part of me has a little bit different, and it's average across. You're doomed. There's nothing to know. Right? And it turns out that we can actually extend this. If you widen this here, it'll start shrinking from here. Such that you can switch it off. If you know this one exactly, you will have a straight line the other way. So there is a flip of this. If you have delta of S here, you have 1 over here. Because it's just Heisenberg uncertainty is a really fancy way of showing this property.
So delta of S is equivalent to 1.
Yeah, you can just reverse it. And there's in-betweens on there, and it's you know, got all kinds of fun stuff. But I'm not going to go through there. There's a square function, and it goes to a sinc function. So if you have a rect, it's going to transpose to sinc. And this distribution carries off, but it's damping down. And the tighter you get this, the more that spike comes up and these damp off.
Right. Okay.
And the wider this one goes, the wider this goes, the more that goes up. The tighter in this one goes, the more it spreads and becomes 1. So you can get them either way. But we don't, that's kind of a big thing often.
So in the extended, though, that would actually damp out at the ends of infinity, right?
Yeah, you just
It would
extend
actually-
the main lobe that goes on just will continue to stretch and it'll push out to infinity.
Right. But it would actually damp at infinity, even if that was a crisp 100%.
In order for it, technically, so this is 1,
Yeah.
you know, but you've got to have that it converges. So 1 times e to the minus st, you know, you must have that your s is able to dampen out. But it, I mean, that's why I've got that minus sigma.
Okay.
Right, the minus sigma allows me to dampen. Because 1 is a constant. 1 times e to the minus sigma right, of t is going to give me a function that damps down to 0. If you didn't have it damped down, if the net product didn't damp down to 0 at infinities, you would have an infinite integral and it wouldn't converge. So that was part of kind of the fun of this. All right. So far, so good? Let's do, real quick, what happens if I have like sines or cosines? Okay. Sines or cosines? Let's say cosine of omega t. Fair?
Okay.
Cosine of omega t, anybody remember what that's equal to?
Minus over 2.
Plus
Right, cosine is even.
cosine's even.
I forgot too. I was like, oh no, it's totally minus.
Right, it'll be minus for the sine. We feel good with that?
Yeah.
Well, now all I have to do is stick this in here. And this is a lot nicer. Right, so when I do the cosine, as it goes on, well, that's just integral 0 to infinity, 1/2 e to the j omega t plus 1/2 e to the minus j omega t times e to the minus st dt. To infinity, and now I can distribute this. So I get 1/2 e to the j omega t e to the minus st plus 1/2 e to the minus j omega t times e to the minus st dt. But notice, common base, I can stick them together, can't I? Okay. So on this one right here, right, so I can separate this up into two ones. I can integrate this one, and then I can integrate that one. We agree? Mm-hmm. So let's just do the one on the left for a sec. It's the integral 0 to infinity of, I'll pull the 1/2 out, e to the minus j omega t minus st dt. You agree?
Mm-hmm.
But that equal to 1/2 of e to the minus s plus j omega t dt. In terms of t, this is just a constant, right? So, I can treat this whole thing as a constant here. So what is the integral of e to the at?
A e to the t.
There's 1 over a e to the at, right?
Yeah.
With the integral limits. And a is just that constant. Well, that's what this is.
Yeah.
So using that, I have 1/2. That's my bottom. 1 over minus s plus j omega times e minus s plus j omega t, evaluated from 0 to infinity. Now at infinity, right, I've got e to the minus something to the infinity. So I'm at e to the minus infinity. That's just 0.
Yeah.
Right? Minus, put this in at 0, this whole thing becomes 0 on top, which means it's e to the 0 whole 1. So what I get is minus this. 1/2 1 over s plus j omega. That's the left one. Right? The right one, the only difference is instead of j omega, it's got minus j omega. That's just a difference in sign.
So a different infinity.
Right? So what you'll get for the other side is j omega just gets negated.
Well,
Didn't
your
you do the
infinity
right one
changes
first?
too. You go then to a positive infinity instead, right? Yeah, so if you distribute...
But this infinity, it's
I'm
minus,
sorry. You're right.
because it's not the oscillation that's killing it.
Right.
It's this that has the real part. It's the damping that is causing it to go to 0, and I didn't change the damping. You changed the frequency of oscillation. Well, I care.
Sneaky.
Doesn't change anything. All it changes is the sign. Right?
Maybe.
So what you end up with for this one, as we're going through, right, it's just this equals this, that's equal to 1/2 times 1 over s plus j omega, right, plus 1 over s minus j omega. And sometimes we just leave it like that as it goes on, but we can also combine it together. All right. To get a common denominator, you notice something kind of neat about this.
Yeah.
They're complex conjugates, right?
Yep.
So if I multiply this one by s minus j omega, top and bottom, I would have s minus j omega for this one times s plus omega squared, or s squared plus omega squared. You agree that's this, times its complex conjugate, top and bottom? And this one times its complex conjugate, top and bottom, gives me s plus j omega all over s squared plus omega squared. Multiply this complex conjugate, top and bottom, I get this. Okay? Common denominator, I get s plus s is 2s times 1/2. I just get s. Minus j omega plus j omega is 0. So I just get s over that bottom. S plus s is 2s times 1/2. Wow. I mean, it's awesome. If you really think about it for a second, it's a piece of beauty that goes on. I mean, this is actually an algebraic function that's not transcendental, that describes a transcendental function. I mean, at some level, the coolness of that has to sink in. You know, it's really some pretty profound stuff that's going on here. I can deal with what otherwise looks like really complex, ugly trig functions as a very simple algebraic one, and it all required that Euler's thing. That's why I spent the time on it earlier on, was because it's very, very helpful to us to understand. If you want to go further into this, take a real analysis course. You'll see all kinds of really cool stuff. We feel good? Realize, and I'll leave this because we're at time, I'll leave this kind of as a fun exercise for you guys. And I really do. And normally that means this is way too difficult to do. But if, in this case, it doesn't, do sine.
Oh, yeah.
Right? I mean, sine, all you do is you're flipping this and you're sticking a j down here. Okay? So it's not really a horrible complexity that goes in. And when you break up the pieces, you'll just get, an imaginary coefficient and some other stuff, and it'll all kind of work out nicely because you're multiplying by complex conjugates. You'll end up with the same denominator, slightly different numerator, right? But it'll still end up being a very beautiful numerator relative to your terms. And then you can take a look at those expressions and take a look at what happens when you combine them together or take derivatives. It's a lot of stuff is explained down. Okay. We feel good? Mm-hmm. Awesome. So this gives you kind of an introduction to the Laplace transform, why it's so bitchin' awesome, and we'll go on using it next time.